Film thickness and uniformity metrology. In the semiconductor industry, controlling film thickness and uniformity is critical for device performance and manufacturing reliability. This presentation focuses on metrology, the science of measurement, as it applies to thin films. Precision measurement technologies are essential to accurately monitor and control these films during deposition processes like chemical vapor deposition, CVD, or atomic layer deposition, ALD. Even minor variations in thickness can lead to electrical performance issues or device failure. Metrology enables consistent quality control, which supports manufacturing excellence by ensuring that wafers meet strict specifications. Additionally, understanding and applying industry standards and best practices ensures alignment with global benchmarks, which helps reduce variability between fabs and suppliers. Whether you're a technician monitoring tools, an engineer optimizing recipes, or a manager overseeing operations, mastering these concepts is key to achieving high yields and maintaining process control. Why metrology matters. Metrology is the critical foundation of semiconductor manufacturing, driven by the extreme precision and control required at nanoscale levels. With shrinking dimensions now reaching 3 nanometers, tolerances must be held within plus or minus 0.1 nanometers. This level of control is essential to continue following Moore's law and to maintain transistor performance and reliability. Precision demands in zero-defect manufacturing mean that defect rate targets are often below 1 part per million, with required measurement precision reaching subatomic levels. Time is also a critical factor. Modern semiconductor processes involve over 1,000 steps, each requiring real-time measurement and process control. Economically, the stakes are high. A single wafer can be worth over $15,000, and any quality failure could cost 10 times the original value in rework. Altogether, the industry requires nanometer, level scale precision, 99.999999% yield accuracy, and supports billions in economic value through robust metrology. What is film thickness and uniformity metrology? Film thickness and uniformity metrology refers to the precise measurement of thin film properties used in semiconductor devices. Film thickness measures the vertical distance between the film surface and the substrate, typically ranging from 1 nanometer to 10 micrometers. To meet industry standards, accuracy must be within plus or minus 0.1 nanometers. Uniformity evaluates how consistent that thickness is across the wafer surface. To achieve reliable performance, the target uniformity is often less than 1%, measured at over 100 points on each wafer. Metrology, as the science of measurement, enables systematic characterization. It uses non-destructive testing methods and allows for real-time monitoring during production. Key parameters include thickness, uniformity, refractive index, composition, surface quality, and film stress. These measurements are essential for process optimization, device performance, and yield enhancement in semiconductor manufacturing. What is film thickness and uniformity metrology? Film thickness and uniformity metrology is essential for accurately measuring the properties of thin films in semiconductor devices. These measurements must be made with atomic scale precision, often down to fractions of a nanometer, to ensure that each layer functions properly within the device. The process must be non-destructive, meaning measurements do not damage the wafer or interfere with subsequent steps. This is critical for maintaining throughput and reducing scrap. Real-time monitoring is another key aspect. It allows engineers and technicians to detect deviations and make corrections during processing, not after the fact. Finally, metrology plays a central role in quality control. Consistent and precise measurements help verify that processes are in control and meet specifications, ensuring reliable device performance and high yield. Together, these capabilities support efficient manufacturing, minimize defects, and uphold the quality standards of advanced semiconductor production. Common measurement techniques. Advanced semiconductor metrology relies on precise, non-destructive technologies to characterize thin films. Two of the most widely used techniques are ellipsometry and reflectometry. Ellipsometry uses optical polarization analysis to determine film thickness and refractive index. It offers exceptional accuracy, up to plus or minus 0.1 angstroms, and can measure a broad range from 1 angstrom to 10 micrometers. It operates in real time, making it ideal for dynamic monitoring, and can handle multi-layer stacks effectively. Reflectometry, on the other hand, analyzes spectral reflection to assess film properties. Though slightly less accurate, at plus or minus 1 angstrom, it is still highly reliable and fast. Its measurement range typically spans from 10 angstroms to 1 micrometer. Like ellipsometry, it is non-destructive and supports both thickness and uniformity evaluation. Reflectometry is also widely used for process control. Together, these tools help ensure films meet specifications, contributing to high yields and reliable device performance. Common measurement techniques. In semiconductor manufacturing, precise film characterization is critical to process control and quality assurance. X-ray methods, such as XPS, XRF, and XRR, offer non-destructive analysis with moderate speed and an accuracy of plus or minus 0.50. These techniques cover a measurement range from 1 µ to 1 making them ideal for analyzing film composition, thickness, and density. They are particularly suited for compositional analysis due to their ability to detect elemental and structural information without altering the sample. On the other hand, scanning probe methods, like atomic force microscopy, AFM, and scanning tunneling microscopy, STM, provide extremely high-resolution imaging with unmatched accuracy, reaching plus or minus 0.010. Although slower in speed, these methods excel in characterizing topography, step heights, and generating 3D surface maps. They are also non-destructive and span a similar measurement range from angstrom to micrometer scale. Each method has its strengths. Optical techniques are fast and contact-free. X-ray methods focus on composition. Mechanical methods offer highest resolution, and hybrid systems combine multiple advantages to enhance characterization. These diverse technologies support advanced metrology throughout semiconductor processing. Challenges and considerations. Achieving accurate and reliable film measurements in semiconductor manufacturing requires addressing both technical and environmental challenges. The first major consideration is meeting strict accuracy requirements. Advanced technology nodes demand sub-angstrom precision, with target tolerances as tight as plus or minus 0.10. To meet this, the industry has developed tools capable of achieving plus or minus 0.050 accuracy for advanced nodes, plus or minus 0.10 for standard production, and around plus or minus 0.50 for legacy processes. These precision levels are critical as even the slightest deviation can impact device performance and yield. Environmental factors are equally important. Temperature stability must be tightly controlled, typically within plus or minus 0.1 degrees Celsius, because thermal drift can alter refractive indices, compromising optical measurements. Vibrations must be kept under 1 since mechanical disturbances degrade measurement accuracy. Finally, maintaining Class 10 cleanroom conditions is essential. Even minor particle contamination can introduce artifacts that skew data, making cleanliness a non-negotiable aspect of metrology reliability. Challenges and considerations. In film measurement, balancing speed and precision is a fundamental trade-off. High-speed measurements are essential for real-time monitoring and process control, where throughput is prioritized. These methods typically achieve accuracies in the plus or minus 1 to plus or minus 50 range, which is sufficient for many production line decisions. However, when ultra-high accuracy is needed, such as in research and development or final quality assurance, high-precision tools are preferred. These can achieve plus or minus 0.10 accuracy, but at slower speeds. The ideal balance point depends on the application, with metrology engineers needing to decide between speed and resolution. Another challenge lies in technical complexity, particularly with multi-layer film stacks. Optical interference between layers can distort results, if not properly accounted for. Material property variations and interface roughness further complicate measurements. Accurate interpretation requires advanced models to differentiate between signal contributions from individual layers. Together, these challenges, critical tolerances, trade-offs, environmental controls, and structural complexity, demand a highly coordinated measurement strategy across both process and metrology teams. Applications and use cases. Accurate metrology plays a vital role across different segments of semiconductor manufacturing. In CMOS logic, which powers advanced node processors, technology nodes have progressed from 7 nanometers to 5 nanometers and now to 3 nanometers. These shrinking dimensions bring increased complexity. For example, gate oxides now measure just 1 to 2 nanometers, while metal layers may number between 15 and 20 per chip. With such dense architectures, tight tolerances of plus or minus 0.05 angstroms are required, and film uniformity must stay below 0.5%. Metrology must be extremely precise to meet these demands, ensuring high performance and yield. Meanwhile, emerging technologies like FinFETs, GAA transistors, and quantum devices introduce new structural challenges. Devices now range from 2D planar FETs to 3D FinFETs and gate-all-around GAA designs. GAA channels are just 3 to 7 nanometers wide and require full 360-degree gate wrap for effective electrostatic control. Spacer layers, critical to these structures, must be measured to plus or minus 0.1 nanometer accuracy. Achieving conformality greater than 95% is essential for reliable transistor operation. These applications underline the importance of advanced, high-accuracy metrology systems tailored for both current and next-generation device architectures. Applications and use cases. Film metrology is essential in supporting memory and analog device performance. In memory devices, metrology ensures tight process control across dynamic random access, memory, 3D NAND devices, and emerging non-volatile memory such as ReRAM. Dynamic random access memory capacitors require uniform dielectric thickness for reliable charge storage. In 3D NAND devices, vertical integration introduces added complexity, with over 128 layers now standard in modern devices. Each layer ranges from 10 to 50 nanometers in thickness, and maintaining 1% uniformity across the wafer is critical. For ReRAM, resistance-based switching depends on precise control of ultra-thin layers and critical dimensions below 20 nanometers. In power and analog applications, different requirements apply. Power devices such as LDMOS and gallium nitride operate under high voltages ranging from 650 to 1200 volts and require thick oxide layers for insulation and reliability. RF and analog devices, including BICMOS and SiGe technologies, operate at gigahertz frequencies, where precise layer matching becomes crucial. The layer thicknesses span a wide range: gate layers around 50 nanometers, oxides up to 100 nanometers, metals at 2 and nitrides at 200 nanometers. Accurate thickness measurements are essential to ensure signal integrity, performance, and long-term device reliability. Applications and use cases. Semiconductor manufacturing relies on precise metrology for quality, performance, and yield. This spans across various device categories, each with unique requirements. Logic devices, such as processors and systems on chips, operate at nodes ranging from 3 nanometers to 28 nanometers. These advanced nodes demand nanoscale accuracy in feature control. Memory devices like dynamic random access, memory, NAND devices, and non-volatile memory require precision across over 128 layers. As stacking density increases, uniformity becomes critical. Emerging technologies, including FinFETs, gate-all-around structures, and quantum devices push boundaries further into the sub-3 nanometer regime. These require metrology solutions that can handle novel architectures and atomic scale dimensions. Power devices, such as LDMOS, gallium nitride, and silicon carbide, operate at high voltages from 650 volts to 1200 volts, needing reliability and robustness. Lastly, RF and analog devices, including BiCMOS and silicon germanium, are designed for gigahertz range operation, requiring accurate control of frequency-sensitive features. Together, these applications highlight the vital role of metrology across the semiconductor landscape. Quality control and process monitoring. Maintaining high quality in semiconductor manufacturing depends on robust process monitoring and real-time feedback. Inline measurement plays a crucial role by enabling continuous monitoring of the production process. It ensures 100% wafer coverage, capturing data from every wafer to prevent defects. With a measurement time of less than 1 second, the system delivers near instantaneous results, which are essential for timely adjustments. Operating 24/7, this technology provides around-the-clock oversight, allowing continuous improvement and reduced downtime. These real-time capabilities support statistical process control and promote consistent output. On the right, yield optimization is highlighted with a current yield of 98.5%, indicating strong process efficiency. Out of every 1,000 wafers, 985 are defect-free, while only 15 show defects. Key metrics also include uniformity, with less than 0.5% variation and accuracy within plus or minus 0.1 angstroms. Together, these tools significantly improve yield, reduce scrap, and ensure process stability. Quality control and process monitoring. Effective quality control in semiconductor fabrication relies on both statistical analysis and dynamic response systems. On the left, statistical process control, or SPC, uses control charts to monitor trends over time. Each data point represents a process measurement, and control limits, defined as plus or minus 3 standard deviations, help determine whether the process is stable or drifting. The center line marks the process target, while the upper control limit, UCL, and lower control limit, LCL, define acceptable variation. This trending enables early detection of anomalies before they become defects. On the right, feedback control enables automated process adjustments. Measurements are continuously fed to a controller, which modifies process parameters in real time. This feedback loop has a rapid response time of under 500 milliseconds, ensuring swift corrections. The system maintains stability greater than 99.9%, with a plus or minus 5% adjustment range. Together, SPC and feedback control deliver high-precision, self-correcting manufacturing that supports both yield and reliability. Quality control and process monitoring. Modern semiconductor manufacturing demands highly responsive, precise, and efficient control systems. Real-time process monitoring delivers immediate feedback with sub-second response times. This rapid feedback loop ensures that process variations are caught and addressed before they impact device quality. Statistical process control, or SPC, supports this by providing ongoing analysis within plus or minus 3 sigma control limits. By identifying trends and deviations early, SPC minimizes waste and ensures process consistency. High yield is another key outcome of effective monitoring. Typical yields exceed 98%, reflecting optimized process efficiency and reduced defectivity. This level of performance is especially critical at advanced technology nodes. Lastly, automation ties all elements together through closed-loop control systems. These systems make adjustments automatically, reducing the need for human intervention. The combination of real-time detection, statistical insights, high-yield performance, and automation enables semiconductor fabs to maintain world-class quality while operating at scale with maximum efficiency. Future trends and emerging technologies. As semiconductor manufacturing advances, metrology is evolving to meet new challenges. From 2024 to 2025, the focus is on AI/ML integration. Intelligent metrology systems are being deployed to provide predictive analytics and auto-optimization. Predictive analytics enables early warning of process drift and potential defects, allowing for proactive corrections. Auto-optimization supports real-time recipe tuning and dynamic adjustment of process parameters. These innovations can improve measurement accuracy by 10 to 50 times compared to traditional methods. Looking ahead to 2026-2027, quantum materials like 2D materials and biomaterials become central. These include atomically thin materials such as graphene and molybdenum disulfide, MOS2, which measure only 0.3 to 1 nanometer in thickness. Quantum dots, another frontier, range from 2 to 10 nanometers. Measuring these requires atomic-level resolution. By 2028-2030, next-generation tools will be essential, and by 2030+, full integration of these technologies into mainstream manufacturing is expected, enabling a new era of precision and control. Future trends and emerging technologies. The semiconductor industry is rapidly evolving, driven by groundbreaking advancements in both measurement technologies and smart factory integration. On the measurement front, next-generation techniques are enabling unprecedented precision and capability. Coherent X-ray systems provide sub-nanometer 3D imaging, pushing beyond conventional limits. Quantum sensing allows for the detection of individual atoms, a game-changer for nanoscale diagnostics. Machine learning-powered spectroscopy introduces intelligent analysis, capable of recognizing subtle patterns and anomalies. Multimodal approaches combine several measurement techniques, providing comprehensive and high-fidelity insights into materials and processes. Meanwhile, Industry 4.0 is transforming manufacturing through smart factory integration. Key enablers include cloud analytics, IoT connectivity, and digital twins, virtual models that mirror real-world operations. These technologies collectively deliver 30–50% efficiency gains. The broader transformation is marked by AI-driven improvements, quantum precision, multimodal techniques, connected environments, and revolutionary changes forecasted for the next decade. Together, they redefine what's possible in semiconductor manufacturing. Metrology is the foundation of semiconductor excellence. Metrology plays a foundational role in semiconductor manufacturing, enabling the precision and control needed for cutting-edge device fabrication. Key areas we've explored include the fundamentals of film thickness metrology, understanding what it is and why it matters. We covered common techniques such as ellipsometry, XPS, SEM, and AFM, each offering unique strengths in measuring critical film properties. But this field also faces challenges. Accuracy, speed, and uniformity remain constant hurdles that must be overcome to meet the industry's demanding standards. Metrology supports applications across CMOS technologies, memory devices, and new emerging tech platforms. Looking forward, the future lies in AI, quantum technologies, and integration with Industry 4.0 systems. On the benefit side, the impact is clear. Metrology contributes to achieving over 98% production yield with measurement precision down to plus or minus 0.1 angstroms. It enables sub-second speed for real-time process control and supports 24/7 operation. The result: improved quality assurance, reduced costs, innovation acceleration, and competitive advantage, driving defect prevention, next-gen device development, and ultimately, market leadership. Why metrology is critical. Metrology is the bedrock of semiconductor manufacturing, providing the precision and control necessary to sustain innovation and economic viability. It enables Moore's law by allowing the continued scaling of device features, which leads to improved performance and higher transistor densities. As devices shrink and complexity increases, metrology ensures every layer and structure is fabricated within exacting tolerances. From an economic perspective, precise measurements reduce waste, maximize yield, and help control manufacturing costs, making production more sustainable and efficient. Metrology also fuels innovation. It enables the integration of new materials and architectures, pushing the boundaries of what is technologically possible. Looking ahead, the next decade brings a future outlook defined by dramatic improvements, accuracy gains ranging from 10 to 50 times. This leap will be powered by AI-driven smart metrology, delivering automated analysis and decision-making. Quantum technologies will enable atomic-level precision. Meanwhile, connected systems, hallmarks of Industry 4.0, will ensure real-time data flow across integrated platforms. Together, these advances promise to redefine the capabilities and role of metrology in advanced semiconductor manufacturing. Film thickness metrology enables technological progress. Film thickness metrology goes far beyond simple measurement. It plays a central role in enabling progress across the semiconductor landscape. By ensuring that every layer of a semiconductor device is fabricated with sub-angstrom precision, metrology supports the scaling required to uphold Moore's law. But its impact doesn't stop there. It also facilitates breakthroughs in quantum computing and artificial intelligence by allowing next-generation chips to be manufactured with unmatched accuracy and reliability. This makes metrology an essential, though often invisible, driver of the modern digital world. Precision truly matters. At the atomic level, even a single angstrom can affect device performance. Continuous innovation in this field ensures future technological breakthroughs remain possible. Moreover, metrology's influence extends globally, enabling advanced technologies to reach broader markets. Ultimately, it's not just about how we measure, it's about how those measurements shape the world of tomorrow.